The room is dim, warmed by a small lamp, and the paper on the desk holds the night in place. Pencils whisper over a weather map, slow and patient, while a cup of tea forgets to stay hot. Outside, Britain is wrapped in blackout curtains, and the sky is doing what it always does, moving on without permission. You think forecasting is guessing. It is not. It is listening carefully to tiny clues, a needle on a barometer, a cloud edge softening, a wind that changes its mind. Tonight, with the Sleepless Scientist speaking low, you settle into that quiet office. You follow the observations, the balloons, the maps, and the cautious words that tried to make tomorrow feel less sharp. In this office, weather is not scenery. It is schedule and fuel and whether a ship keeps its shape in the dark. It is whether laundry dries before the next ration line. It is whether a coastal train crawls through fog or pretends it never existed. During the war, forecasts are not for poetry. They are for decisions that have weight and sometimes consequences that arrive before the post does. So you watch the routine begin, because routine is what makes the sky feel measurable. A clerk slides fresh forms across the desk. A forecaster checks a clock that keeps wartime like a heartbeat. Reports come in at set hours because the atmosphere does not care, but people do. And you learn the first quiet truth of forecasting. It is not one brilliant prediction. It is many small observations gathered like coins until you can afford a guess. You stand near the map table and you realize it is not one map. It is layers of paper, replaced, annotated, and pinned down again. Ink stains mark yesterday's confidence. Fresh pencil marks show tonight's caution. Somewhere down the corridor, a telephone rings. Once, then stops. No one rushes. Rushing is how you miss a detail, and details are the only currency here. You imagine weather as something happening over your head, but in the forecasting office, weather begins in your hands. It begins with numbers written by ordinary people, outdoors in damp coats, squinting at instruments that are never as obedient as diagrams suggest. And that is what makes this place strangely comforting. The sky is enormous and indifferent, but the work is small and human and repeatable. A thermometer is checked, a wind vane is watched, a barometer needle is read twice, because the first time you might have wanted it to be different. Some nights the map looks calm, like a held breath. Some nights it looks busy, like a worry you cannot put down. Either way, you are not trying to control the weather. You are only trying to meet it on time. People outside think the forecaster owns tomorrow. In here, you know better. You can only negotiate with it politely, using evidence. And in wartime Britain, evidence arrives through a web of stations scattered across land and coast. Small huts, airfields, harbors, fields that smell of wet soil and coal smoke. Each station is a quiet witness. Each one sends a few facts and then returns to waiting. If a report is missing, the map gains a blank spot like a missing tooth. You do not panic. You compensate. You learn to treat absence as its own kind of information, because wartime is full of absence. Blackout curtains hide cities. Censorship hides ships. The sky hides itself with cloud, and the forecaster learns to live with partial truths. You pick up a pencil, and you feel how little pressure it takes to change a line. That is another quiet truth. Forecasting is powerful and fragile at the same time. A low-pressure system can be drawn a few miles east or west, and that small change can mean rain over an airfield or clear skies for a crossing. So, the pencil moves slowly. Not because the forecaster is unsure, because the forecaster respects how costly certainty can be. And when you look around the room, you notice the faces. Not heroic, not dramatic, just tired people with practiced hands. They have the same posture as accountants and the same patience as librarians. They are building an argument with the atmosphere, one careful step at a time. Their tools are plain: paper, ink, telegraph messages, a telephone line that crackles like a campfire. And behind all that, the real instrument is the habit of observation. Doing the same small thing at the same time, day after day. Even when sirens have interrupted dinner, even when windows are taped and streets are dimmed, even when the mind would rather not think about tomorrow at all. That is why the forecast office feels almost like a sanctuary. Not because it is safe, because it is consistent. And consistency is a kind of shelter. If you stay in this room long enough, you start to sense the goal. It is not to predict the weather perfectly. It is to reduce surprise, to make tomorrow less sharp. As you heard, not blunt, not harmless, just less likely to cut unexpectedly. So the team works with humble ambition. They want to know when the wind will turn, when pressure will drop, when cloud will thicken into rain, or thin into a bright, bitter morning. They want to know, in plain terms, whether people should expect trouble. And because people love simple answers, the forecaster learns to translate complexity into short phrases. But that part comes later. First, you have to earn those phrases, and you earn them by going back to where the weather begins, which is outside, on the ground, in the air that touches your face. So you leave the map table for a moment. You step out quietly into a small yard behind a station. The night air feels damp and slightly metallic, like it has been stored near rail tracks. Somewhere nearby, the sea is breathing against the coast. Even if you cannot see it, you look for the instruments, because instruments are how you make the invisible behave. There's a thermometer screen painted white with slatted sides. It looks innocent. It is not decoration. It is a compromise. The screen keeps sunlight off the thermometer in daytime and keeps rain from lying to it at night. Even so, it is never perfect. Wind sneaks in, moisture lingers, and the person reading it brings their own warmth, their own breath, their own impatience. So you read it with care. Air temperature is a simple number that hides a complicated story. It is the average energy of molecules, a restless crowd of nitrogen and oxygen bumping into each other in the dark. Tonight, they are moving a little slower. You can feel it in your fingers. Cool air does not announce itself loudly. It just steals heat from you, steadily, like a quiet thief. Nearby, a second thermometer might wait lower down, closer to grass. That one often reads colder at night because the ground loses heat to the sky and the air near it cools first. This is how frost forms, even when the official air temperature seems too mild for it. The atmosphere loves these small tricks, and the forecaster learns to respect them because people do not slip on charts. They slip on icy steps. You turn toward the wind vane. It creaks softly and points with its whole body. Wind direction is one of the most practical observations there is. Wind tells you where air came from the Atlantic, damp and busy. From the continent, drier, sometimes colder, sometimes carrying haze. From the north, crisp and impatient. From the south, often mild, occasionally smug. You hold your face slightly into it because your skin reads wind faster than your mind. And then you look at the anemometer, the little cups that spin. They do not spin for drama. They spin because air is moving, and movement is the atmosphere's favorite habit. Wind speed matters for everything that has to travel through it. Aircraft, ships, smoke, even sound. On a calm night, noise feels close, as if the world is listening in. On a windy night, sound is shredded and carried away. A forecaster notices this without trying, not because it is romantic, because it is useful. Then there is the barometer, often indoors, mounted like a piece of respectable furniture. People like to pretend it is mystical. It is not. It is a weight scale for the sky, not the whole sky, of course. Just the column of air stacked above you, pressing down constantly, like a hand you have learned to ignore. The barometer needle rises when the air above you is heavier, more piled up. It falls when the air is lighter, when it has been lifted and stirred and thinned by weather systems passing through. A falling barometer often hints at unsettled weather coming, not because low pressure creates rain by magic, because low pressure usually means air is rising, and rising air cools, and cool air cannot hold as much water vapor. So the vapor condenses into cloud, and if cloud thickens enough, it stops being decoration and becomes rain. You watch the needle closely, not just the value, but the trend. Is it steady? Is it drifting? Is it dropping with determination? In forecasting, change is often louder than the absolute number. A steady low can mean a stubborn system sitting overhead. A rapid fall can mean something energetic approaching, a system with wind and personality. And because the war has trained everyone to look for patterns, you notice how comforting this is. Here is a threat that can be measured, not perfectly, not completely, but enough to speak about it with calm words. That is what these observations offer. They turn dread into data. Not all dread, of course, just the portion that comes from the atmosphere. And the observations are not random. They follow a schedule, like prayers said at fixed hours. Stations report at agreed times. Morning, afternoon, evening, night. Each report is short. Temperature, pressure, wind, cloud amount described in simple fractions. Visibility, a surprisingly important detail in a country that runs on travel and secrecy. Present weather, a phrase that can mean drizzle, fog, snow grains, or rain so fine it feels like the air itself is leaking. This rhythm is part of what kept forecasting possible. If everyone reports at different times, you cannot draw a real picture. You just get anecdotes. So the world agrees, quietly, to look at the sky together. And those small coordinated glances become a map. But the network is never complete. Some stations are remote. Some are damaged. Some are simply overwhelmed by the same weather they are trying to measure. Fog can hide the horizon so completely that estimating cloud height becomes guesswork. A strong gust can shake a rain gauge, and the water inside sloshes like a temperamental pet. In winter, instruments ice over. In coastal air, salt creeps into mechanisms and makes them stiff. And there is always human error, the gentle sort, a hurried reading, a smudged number, a report sent late. Forecasting offices know this, and they do not take it personally. They build habits to catch mistakes. They compare neighboring stations. They look for values that do not make sense next to each other. If one station reports clear skies and the next reports heavy rain, someone asks a quiet question. Sometimes the answer is simple. A shower can be narrow and miss one station entirely. Weather loves to be patchy. But sometimes the answer is a misread instrument or a telegraph error. So the map is built like a quilt, with careful stitching and a few inevitable gaps. And you begin to appreciate how much of forecasting is not prediction at all. It is quality control for reality. It is deciding which pieces of information deserve trust. Not because people are dishonest, because the world is messy, and measurement is a human act. Back in the forecast office, those observations arrive like small parcels, some by telephone, some by telegraph, some by written reports carried along ordinary routes. They are transcribed, sometimes by hand, into neat forms that make chaos look polite. Each station's numbers are placed on the map in a standardized pattern, so any forecaster can glance and understand. This is one of the quiet miracles of the craft, a shared language of symbols, a way to compress the sky into marks on paper, a way to make distant wind and cloud feel close enough to touch. You watch someone write a station model, those clustered little numbers and symbols, a circle for cloud cover, a barb for wind direction and speed, tiny codes for rain or fog. To an outsider, it looks like secret writing. To the forecaster, it is a sentence. And once enough sentences are written, the story begins to appear. But it is a slow story, not a plot twist, more like a tide coming in. You can see the pressure values across the country, higher here, lower there, a gradient of weight across the landscape. And where pressure changes quickly over distance, winds tend to be stronger. Air moves from higher pressure toward lower pressure, but it never goes straight because Earth rotates, and that rotation bends the path like a gentle but stubborn hand on the shoulder. This is called the Coriolis effect, a name that sounds fancy and feels simple. If you try to roll a ball across a spinning carousel, it curves. The ball is not choosing drama. It is just moving on a moving surface. So winds curve around pressure systems, and the patterns repeat often enough that humans can learn them. This is why forecasting is possible at all. Not because the atmosphere is predictable like a clock, because it is predictable like a habit, often reliable, sometimes moody, always capable of surprise. In Britain, the main mood comes from the west. The Atlantic is a generous machine, constantly feeding air with moisture and motion. Low-pressure systems form and travel, like travelers with luggage, arriving with fronts and cloud bands. And the forecaster watches for them, the way you watch for a friend who always shows up late, but always shows up. Now, you might assume ground observations are enough. Thermometers, barometers, wind vanes. Surely that tells you what you need. But the atmosphere has depth, and most of its decisions are made above your head. The ground is only the bottom of the ocean of air, so if you want to know what is coming, you have to listen upward. And this is where the story becomes quietly strange. Because now, to measure the air, you let something go. A balloon, released into the dark, carrying instruments like a small sacrifice to curiosity. You walk with a meteorological observer to an open space, away from trees and buildings that might snag the line. The balloon is pale, almost luminous in the dim light. It is filled with a gas that wants to rise, either hydrogen or helium when available. Hydrogen is more common in those years, and it is effective. It is also enthusiastic about fire, so the handling is careful and calm and practiced. No sudden movements, no smoking, obviously. You hold the balloon lightly, feeling its upward tug, like it is impatient with Earth. Attached beneath it is a small instrument package, not heavy, just clever. A radiosonde, a word that means radio sounder, though it does not sound anything. It sends measurements back as it climbs. Temperature, pressure, humidity, the amount of water vapor in the air. Humidity is the air's hidden inventory, how much water it is carrying without showing you. Sometimes it carries a lot and pretends it is innocent. Sometimes it carries almost none and still manages to chill you to the bone. The radiosonde measures it with a sensor that changes as it gets damp, and that change becomes a signal. You do not need to love the electronics to appreciate the cruelty of the task. You are asking a moving, invisible fluid to describe itself while it is actively changing shape. As the balloon rises, the air pressure drops and the balloon swells. It grows rounder and tauter, like a secret it cannot keep. It climbs through layers you can barely name, each with its own mood. Near the ground, the air still remembers hedges, chimneys, and wet grass. Higher up, it forgets the details and becomes simpler, colder, and faster. The balloon does not glide. It is carried. It is an obedient passenger in a river you cannot see. And you, standing below, are reduced to watching a pale dot drift into the blackout. You think it is going straight up. Wrong. It is already being stolen sideways by winds that do not care about your neat map. A few minutes pass. The radiosonde chatters back through the receiver, a soft rhythm of data. The numbers arrive as a trace on paper, or as tones that are translated into meaning. You watch the line of temperature, the gentle slope downward as the balloon climbs. Most nights, temperature drops with height, and that feels sensible. Get farther from the warm ground, get colder. But the atmosphere enjoys exceptions. Sometimes the temperature stops dropping and starts rising again for a while. Congratulations, you have found an inversion. An inversion is a lid. It is warm air sitting above cooler air, like a hand pressing down. It traps smoke. It traps fog. It traps the smell of coal and damp stone. It traps you too if you are trying to climb out through cloud in an aircraft. In wartime, inversions matter because they make the sky behave. Not in a helpful way, just in a consistent way. Fog can form under an inversion and refuse to leave even after dawn. A city can smother itself in its own exhaust and call it weather. The balloon keeps climbing. The pressure falls enough that your ears would complain. If you were up there, you are not up there. You are down here, warm enough, holding a clipboard, listening to the upper air confess. And the upper air has a different personality. It is less polite. It is more decisive. Down low, wind is bullied by trees and buildings. Up high, wind becomes what it wanted to be all along. Fast, straight, and busy. The radio sonde lets you estimate wind by tracking the balloon's drift. You watch it with a theodolite, a careful little telescope on a stand. You follow the dot, you measure angles, you do it again and again. From those angles and times, you can calculate how the wind is pushing the balloon. It is slow work. It is also the difference between guessing and knowing, because wind up there is not just wind. It is steering. It is the conveyor belt that carries storms from the Atlantic toward your coastline. It is the reason a calm evening can become a wet morning without anyone voting for it. Sometimes the balloon disappears into cloud. You lose sight of it, but the radio keeps talking. The sky can hide the messenger, but it cannot fully silence the message. Other times, the radio fades. Static, a crackle, a sudden emptiness. The balloon may have burst early, or the battery may have frozen, or the antenna may have been damaged. It happens. The atmosphere is not required to cooperate with your schedule. So, you make a note and you continue anyway, because this is what forecasting teaches you, gently and repeatedly. You never get all the information. You only get enough to make a careful decision. Back in the office, upper air observations are treated with respect. They are not decoration. They explain why the surface is doing what it is doing, or about to do. A rising warm layer can signal an approaching front. A strong wind shift aloft can mean the whole system is turning. And in those years, with aviation becoming an everyday necessity, upper air becomes precious. Pilots care about cloud bases, icing, turbulence, and the simple question of whether the sky is lying. An aircraft does not care that fog is romantic. An aircraft cares that fog is a wall. So observers also watch clouds with the devotion of people watching a complicated machine. Not for beauty, for hints. Low clouds, the ones that hang like wet wool, often mean stable, saturated air. Stratus, the flat gray sheets, can sit for hours and drain your patience. They form when air is lifted gently or cooled from below until it cannot keep its water invisible. If there is drizzle, it often comes from this kind of cloud. Drizzle is rain that cannot commit. It is the atmosphere tapping you on the shoulder for an entire afternoon. Then there are the puffy clouds, the ones with edges, cumulus, little heaps, like the sky is piling laundry. Those can be harmless, or they can be the start of something more energetic. If the air is unstable, if warm air near the ground can rise freely, those heaps grow. They stack upward. They darken underneath. They become cumulonimbus, the tall towers with flat tops. And in those towers, water and ice collide and separate. Charge. Lightning is not magic. It is the atmosphere balancing its books violently. You do not need a thunderstorm to make war feel dramatic, but war appreciates the extra ambiance. High clouds are another language. Cirrus, thin and feathery, often arrive ahead of a warm front. They are made of ice crystals, high enough that the air is bitterly cold. They can mean that moisture is arriving aloft, even if the ground still feels calm. So, you learn to treat them like distant footsteps. Not a guarantee, just a warning. Altostratus, a thicker veil, can turn the sun into a pale coin. That often means the front is closer now, the moisture deeper. And then nimbostratus, the thick gray that does not bother with texture. That is steady rain, the kind that erases edges and makes roads shine. In Britain, steady rain is not an event. It is a season that visits whenever it wants. All these observations, surface and upper air, arrive in the same place. The office, the map table, the pencil. And now you watch the transformation that makes meteorology feel like storytelling. You take scattered facts and you draw something continuous. You do not invent the lines. You suggest them. You look at pressure readings across the stations and you connect equal values with smooth curves. Isobars, a word that means equal pressure, and in human language means the sky's invisible topography, like contour lines on a hill map, but the hills are made of air weight. When isobars are far apart, the pressure changes slowly across distance. Winds tend to be lighter. When isobars crowd together, pressure changes quickly. Winds pick up. The atmosphere hates a gradient and tries to fix it. Air accelerates, and you hear it in tree branches, in windows, in the restless sound of the night. But because of Earth's rotation, winds do not just rush inward toward low pressure. They curve. In the northern hemisphere, they spiral counterclockwise around a low. They spiral clockwise around a high. It is a pattern that repeats enough to become comfort. Not comforting in the way a blanket is comforting. Comforting in the way a predictable threat is comforting. At least you know how it moves. You draw a low and you imagine air rising there. Rising air cools and cooling makes cloud. So lows are often cloudy, wet, and unsettled. Not always, but often enough to be useful. You draw a high and you imagine air sinking. Sinking air warms, and warming dissolves cloud. So highs often mean clearer skies, calmer winds, and colder nights in winter because heat escapes. Again, not always, but enough. Then come the fronts. Fronts are boundaries between different air masses, not walls, more like seams, where warm air and cold air meet and argue about who gets to stay. A warm front is warm air advancing, gliding up over cooler air. It is polite in a slow, suffocating way. It brings a gradual thickening of cloud, then steady rain. A cold front is cold air advancing, pushing under warm air like a wedge. It is less polite. It can bring sharp showers, gusts, a sudden temperature drop, and a clearing behind. You mark these fronts on the map with symbols, triangles for cold fronts, semicircles for warm fronts, because humans like little pictures. And now the map looks alive. Not alive like an animal, alive like a machine running. Lines curve and cross. Pressure centers drift. You can almost feel the Atlantic pushing, sending systems eastward like a conveyor. You think the map is the weather. It is not. It is a frozen moment, and the atmosphere is already leaving it behind. So the forecaster's job is to imagine the next map, to take this still image and make it move, and to do that, you rely on experience and on the simplest physics that still works at midnight. You look at the spacing of isobars and the shape of the troughs, those elongated regions of low pressure. You look at the upper wind because it often leads the surface. If the winds aloft are strong, systems tend to move faster. If the upper pattern is blocked, if high pressure is parked stubbornly, systems can stall. A stalled system is a kind of slow torture. Rain that will not leave, cloud that will not lift, mud that deepens with patience. In war, mud is not poetic either. Mud is transport delayed, aircraft grounded, boots ruined, morale irritated. So you care where the lows will go and how quickly. In those days, over the ocean, information is thinner. There are ships, yes, and coastal stations, and occasional reports from aircraft. But the Atlantic is wide, and war makes silence a strategy. Convoys do not advertise their positions with casual messages, so meteorologists often had to infer what was happening out west from what arrived at Ireland and what the upper air suggested. You learn to read the edge of the picture. You learn that weather often approaches like a rumor. First high clouds, then falling pressure, then wind, backing or veering, depending on the setup. Then the front arrives, and the rumor becomes a wet fact. This is why the ocean matters so much. It is not just a background, it is the engine room. The Atlantic holds heat longer than land because water has a high heat capacity. In plain terms, it takes a lot of energy to warm it, and it gives that energy up slowly. So in winter, the ocean can be relatively warm compared to the land. Air flowing over it can pick up moisture and heat, becoming unstable and eager to form cloud. In summer, the ocean can be cooler than land, and air flowing in can bring sea fog, low cloud, and that damp chill that makes you regret stepping outside. Sea fog is a special kind of quiet hazard. It forms when warm, moist air moves over cooler water and is chilled to its dew point. That is the temperature where air cannot keep all its water vapor invisible anymore. So, the vapor condenses into tiny droplets, suspended, a cloud sitting on the surface. It can roll inland like a slow animal. It can swallow a harbor without sound. For ships, fog means navigation by instruments and nerves. For aircraft, fog means delays, diversions, and sometimes worse. In blackout Britain, fog also means an odd mercy. It hides things. It muffles light. It makes the world smaller, but it also makes accidents easier. Your eyes are not as useful as you wish they were. The coastline itself bends weather. Land and sea heat differently, and that difference drives breezes. By day, land warms faster. Air rises and cooler air flows in from sea. A sea breeze. By night, land cools faster, air over it sinks, and air can flow offshore. A land breeze. These are small circulations, local, but they matter if you are trying to land an aircraft or predict coastal fog. And Britain has a lot of coastline. The atmosphere has many edges to trip over. As you study the map, you begin to see why a forecaster in wartime was rarely bored. Not because the work was thrilling, because the work was relentless. Every few hours, new observations arrive. The map must be updated. The interpretation must be adjusted. And the forecast must be issued in time to matter. This is the gentle cruelty of forecasting. If you wait until you are sure, you are too late. If you speak too early, you risk being wrong. So you learn to live in the middle, where evidence is incomplete, but decisions cannot wait. In the office, the work has a particular soundscape. Paper sliding, pencils tapping, a quiet murmured exchange about a pressure fall at a coastal station. Someone checks the latest upper air plot and frowns, not dramatically, just thoughtfully. The forecaster is not a prophet. They are an accountant for the sky, balancing inputs and outputs. And like any accountant, they are haunted by missing receipts. Now, your mind drifts naturally to the seasons. Because even if war rearranges human schedules, the year keeps turning. And seasonal patterns are the oldest kind of forecast. In winter, the temperature gradient between equator and pole is stronger. That gradient fuels the jet stream, the fast river of air aloft. Stronger jet, more energetic storms. So winter in Britain often feels like a parade of lows, each one arriving from the Atlantic with new rain. The days are short, the nights are long, the ground stays damp. A forecaster in winter learns to respect how quickly conditions can change. A morning that begins with a calm frost can end with sleet driven sideways. Cold air is denser, heavier. It hugs the ground. Warm air rides over it, and fronts become active. Snow becomes possible when cold air is deep enough and moisture arrives at the right time. Snow is not common everywhere, but when it comes, it changes everything. Rail lines, roads, airfields, and because wartime logistics are already strained, snow feels like the atmosphere joining the enemy. Casually, in summer, the gradient is weaker. The jet stream tends to be farther north and often less intense. High-pressure systems can linger. You get stretches of calmer weather, clearer skies, and longer days. But summer is not always gentle. Warm air can hold more water vapor, and when it rises, it can release that moisture in sudden heavy showers. Thunderstorms can pop up with little warning, especially when the air is humid and unstable. And haze becomes a feature. Not fog, not cloud, just the air filled with tiny particles and moisture that scatter light. The distance blurs. The horizon softens. It looks peaceful, but it can hide smoke or aircraft or landmarks. Spring and autumn are the in-between seasons. The atmosphere loves in-between. That is where contrast lives. Warm and cold air masses battle more often. Fronts can be sharper. Winds can swing. A day can contain all four seasons if the right system moves through. These transitional seasons also bring their own quiet hazards. Autumn brings longer nights, cooling ground, and fog that returns with dedication. Spring brings cold nights and deceptively warm afternoons, and the temptation to underestimate how quickly temperature falls after sunset. The forecaster learns to speak of these things without drama, because people need usable information, not poetry. Still, in the background, the war changes what is said and how. Some details are restricted. Some broadcasts are cautious. You do not want to hand an advantage to someone listening. So forecasts can be deliberately vague in public channels, while specific instructions travel privately where needed. And that is another layer of the craft. Not just what the atmosphere is doing, but what you are allowed to admit it is doing. Now, shift your attention downward again. from the grand patterns to the ground itself, because the land beneath the air is not a smooth board. It is hills, valleys, cities, forests, rivers, and coastlines, and each one nudges the air slightly, like fingers shaping clay. When wind meets a hill, it is forced upward. Rising air cools, and cooling makes cloud and rain more likely. So windward slopes can be wetter, leeward sides can be drier. In a rain shadow in Britain, these effects are real, even if the hills are modest compared to mountains elsewhere. The Pennines, the Welsh Hills, the Scottish Highlands, they shape rainfall patterns and cloud, and they create local winds that a big map cannot fully capture. Valleys trap cold air at night. Cold air is denser, and it flows downhill like an invisible liquid. It pools in low places. That is why frost often forms first in hollows, and why fog loves valleys. Radiation fog forms when the ground cools rapidly under clear skies and light winds. The air right above the ground chills to the dew point, and water condenses into droplets. It starts shallow, a thin layer hugging the grass. Then it thickens, it deepens. It becomes a quiet ocean you can walk into and disappear. In a city, the story shifts again. Buildings and stone store heat. They release it slowly at night, so cities can be slightly warmer than the surrounding countryside. This is the urban heat island effect, though no one in the 1940s needed the term to feel it. You step from a rural road into a town, and the air feels different, softer, less likely to frost. But cities also create their own turbulence. Wind funnels through streets. Smoke and soot add particles that water can condense on. Fog can become thicker, dirtier, more persistent. London fog, the famous pea soup, is not just weather. It is weather plus coal. It is droplets clinging to soot, turning the air into a stained curtain. During the war, with industry running and heating needed, those particles are plentiful. So fog forecasts matter. Visibility is not an abstract number. It is how far you can see before the world ends. It is how safely a plane can land. It is whether a driver sees a cyclist or only hears a shout too late. This is where you feel the humility of the forecaster. The big map says a high-pressure system is overhead, so conditions should be calm. And yet, a valley fills with fog anyway. A hilltop is clear, but the airfield below is blind. A coastal station reports a sea breeze that the inland stations do not feel. Local weather is the atmosphere's way of reminding you that averages are not the same as reality. So forecasters build a second map in their minds, not drawn on paper, but remembered. They remember which airfields are fog-prone. They remember which harbors get sudden squalls. They remember how wind behaves in certain valleys. This is not superstition. It is pattern recognition, trained by repetition. And repetition is what the wartime schedule provides. Every day, observations, everyday maps, every day the same arguments with new details. Over time, you begin to feel the office's quiet confidence. Not arrogance, just competence. You can be cynical about humans and still admire a group of them doing careful work in the dark. The atmosphere does not care if your country is at war, but you do, so you keep measuring. Now, with all these inputs, comes the moment that feels simple but is not. You have to speak about tomorrow. You have to turn lines on a map into words that someone can act on. And words are dangerous because people treat them like promises. In the forecast office, the language is practical, useful, cautious, and a little bit unsatisfying because the sky does not sign contracts. You watch the forecaster choose words the way a medic chooses bandages. Not too dramatic, not too thin, and always with an eye on what might bleed through. They do not say, "There will be rain." They say, "Rain at times." They do not say, "Clear skies." They say, "Becoming clearer," because becoming admits motion, and motion is the only honest promise the atmosphere ever keeps. You lean closer to the paper draft of the forecast, and you see how the language is built from shared codes. Changeable, unsettled, bright intervals, occasional showers. These phrases sound like indecision to someone who wants certainty. In the office, they sound like a careful translation of probabilities into something a person can pack for. Changeable means the air is arguing with itself, and you should not trust a single hour. Unsettled means a low is near, and the sky will keep trying new ideas. Bright intervals means the sun will appear briefly, like a shy guest, then slip away again. Occasional showers means clouds will take turns, and some places will be spared by pure luck. You learn that even the most basic word has to be handled gently. Rain can mean a steady sheet, or needle-like drizzle, or a brief, loud burst. Mist is not fog, but it can still make the distance feel dishonest. Windy is not a measurement. It is a warning about loose objects and tired nerves. So the forecaster ties each word back to the map. In their mind, the warm front means thickening cloud, lowering ceilings, visibility that softens. The cold front means a line of showers, gusts, a temperature drop you feel in your wrists. A high means calmer weather, but also the possibility of fog in the morning, and frost that arrives without applause. A slack pressure gradient means light winds, and in Britain, light winds can be a problem, because without wind, smoke lingers, fog forms, and damp air sits in place like a stubborn guest. So the forecast is not a simple good or bad. It is a list of inconveniences and occasionally dangers scheduled as best as the evidence allows. In wartime Britain, there is another quiet constraint. Some forecasts meant for the public are smoothed and simplified, not because meteorologists enjoy vagueness, but because an enemy can read weather too. If you announce precise wind direction and cloud base at a certain hour, you are sharing tactical information for free. So the detail is rationed, like sugar. More precise guidance goes to the people who need it, through quieter channels, airfields, harbors, operations rooms with maps that do not leave the building. You imagine the strange intimacy of it. The sky is a shared environment, but during war, even the sky becomes partly classified. And still, the weather refuses to join any side. It crosses borders without papers. It drifts over the channel with the same indifference it has always had. Now you watch the forecaster commit the words to a form. There is a time window, because a forecast must have an expiration date. If you let it run too long, it becomes a horoscope. So they focus on tomorrow, sometimes the next 2 days, rarely more. Beyond that, in the 1940s, confidence drops quickly, not because the forecaster is weak, but because the atmosphere is chaotic in the true scientific sense. Small differences grow with time. A slightly misplaced front today becomes a completely different rain pattern in 2 days. You can feel the truth of that without needing equations. You have had mornings where the air felt wrong, and by evening, the whole day had drifted off course. The forecaster signs the forecast, not with flourish, but with responsibility. Then it travels outward, to radio, to notice boards, to commanders, to ship routes, to people who will stare at the sky anyway. And now comes the part nobody likes to talk about, because it is the part that proves humility. The error. The forecast that misses by a few hours, or a few miles, or a whole mood. You think errors are rare, the way people prefer to imagine professional work. But in forecasting, errors are normal, and the craft is learning how to live with them. A forecast is a snapshot of a moving system, described in words that cannot hold the whole shape. So the office does not treat mistakes like moral failures. They treat them like feedback. A pressure drop came sooner than expected. A front stalled because the upper flow weakened. A fog bank formed because the ground cooled faster than the model in someone's head assumed. The next map is drawn with that lesson quietly folded in. No speeches, no punishment, just adjustment. And the next scheduled report, that scheduled rhythm matters again here, because the atmosphere does not stop changing while you feel embarrassed. So you update, and you update again. Somewhere between midnight and dawn, you see the most honest attitude a forecaster can have, an acceptance that the goal is not perfection. The goal is to be less wrong than yesterday, and wrong in a useful direction. Now, speaking of useful direction, you follow the forecast out of the office and into the world it was meant for. You picture a coastal airfield with hard ground and dim lights. You are not a hero here. You are an aircraft, cold metal and rivets, waiting for air that behaves. Your wings do not care about patriotism. They care about air density and icing and crosswinds that try to push you sideways on landing. If the forecast says low cloud, your mission becomes a delay or a gamble. If the forecast says gusty winds, your takeoff roll changes, your climb angle changes, your fuel calculations tighten. And if the forecast is wrong, you do not write a polite complaint letter. You become wreckage, or you limp home with a new respect for the difference between predicted and observed. That is the sharp edge beneath the gentle language. In those years, meteorology is not a hobby for people who like clouds. It is a tool, and tools are judged by outcomes. So when forecasters choose cautious words, they are not being timid. They are being honest in a world that punishes overconfidence. You shift again now to the sea. You are a ship in convoy, heavy with cargo and worry. The ocean looks flat in the dark until it does not. Wind over water builds waves with patient mathematics. The longer the wind blows and the more open water it has, the more the waves grow. That open distance is called fetch, a word that sounds like a dog command and behaves like a threat. A wind that has crossed the Atlantic has had plenty of fetch. So when a low approaches, the sea does not simply get rough, it becomes organized violence. Long swell, then short, steep waves on top, then spray that coats everything in salt. Salt finds seams. Salt finds metal. Salt finds skin. A forecast that warns of gales is not just about discomfort. It is about whether a ship can maintain speed, whether smaller escort vessels can keep station, whether decks become too dangerous to work. It is about whether the convoy spreads out and becomes easier to find. So the weather forecast becomes part of strategy, even when nobody wants to admit that strategy depends on clouds. And yet, the forecaster is still using the same pencil, the same isobars, the same missing reports from the ocean. In wartime, ships are often radio silent. That silence keeps them safer from interception, but it also keeps meteorologists partially blind. So they infer, they use coastal pressure trends, they use upper air winds, they use the known behavior of Atlantic depressions, their typical tracks and speeds. They do what humans always do when they cannot see the whole truth. They build a model in the mind and keep checking it against new evidence. Now, if you stay with this long enough, you start to feel the deeper science behind the calm routine. Not the fancy part, not the equations on a chalkboard. The physical reasons the map tends to make sense at all. The atmosphere moves because energy is unevenly distributed. The equator receives more sunlight, more heating. The poles receive less. That difference is the engine, and everything else is plumbing. Air tries to move heat around, and in doing so, it creates winds, fronts, storms, and the endless inconvenience of weather. Earth's rotation turns simple flows into spirals. Moisture turns invisible warmth into clouds you can see, and the ocean stores heat like a slow battery, releasing it at the wrong times, into the wrong places, for the benefit of nobody in particular. Forecasting is the attempt to keep track of that messy heat redistribution in real time. In the 1940s, you do it with limited data and a lot of experience. You do it with hand-plotted maps and telegraphed numbers. You do it while the country is tired and the nights are dark, on purpose. Now, your mind naturally asks, how did they not go mad? The answer is routine and the strange comfort of constraints. Every observation has a format. Every map has a method. Every forecast has a scheduled release. And within that structure, a forecaster can do good work without needing to feel heroic. That is the kind of competence that rarely gets celebrated, and it is exactly the kind that keeps people alive. But the tools do not stay frozen in the 1940s. Even during the war and after it, the slow evolution begins to add new senses to the craft. So you let the pencil and paper sit for a moment, and you drift forward in time, just gently. Not to a shiny future, not to a perfect one, just to a world where meteorologists get new ways to look. Speaking of looking, the first great change is learning to see precipitation before it reaches you. Radar, a word that sounds like a mechanical insect. Radio detection and ranging, translated into human, you send out pulses and listen for echoes. The pulses are radio waves, invisible, traveling fast, passing through air like gossip through a corridor. When those waves hit something, some of them scatter back. Raindrops, snowflakes, hailstones, even insects in some conditions. Because the world enjoys irony. The radar antenna rotates, sweeping the horizon. The receiver measures the time it takes for echoes to return. Time becomes distance. Echo strength becomes a clue about how much stuff is in the air. So instead of waiting for a rain gauge to fill, you can watch a rain band approach. You can see the shape of the storm, its edges, its gaps. In the wartime context, radar is developed for many reasons, including watching aircraft, But weather is always there, cluttering the signal, making itself known. At first, weather echoes are sometimes treated like a nuisance. Congratulations! The atmosphere has found a way to interfere with your technology again. Then someone realizes the nuisance is also information. A radar screen showing blobs and streaks is a map of precipitation in motion. Not perfect, not complete, but immediate. And immediacy is priceless in forecasting, because now you can update warnings faster. You can say, showers approaching from the west, rather than showers likely later. You can track a squall line and estimate when it might hit a harbor. It is not prophecy. It is observation with less delay. But that alone changes the feel of forecasting from slow interpretation to something closer to monitoring a living system. Then you drift forward again, and the next new eye opens above the planet. Satellites. Not in the 1940s, but soon enough that the culture of meteorology transforms. A satellite is a machine in orbit, falling around Earth endlessly, taking pictures of cloud tops. You cannot smell the rain from orbit. You cannot feel the wind on your face. But you can see the swirl of a cyclone, the comma shape of a front, the thin veil of high cloud announcing a system. Visible imagery shows reflected sunlight, so you can watch cloud patterns in daytime. Infrared imagery shows temperature, so you can see clouds at night, because cold cloud tops stand out against warmer surfaces. In human terms, you can finally watch the sky move, even when the ground is asleep. For a forecaster trained on sparse ocean data, this is like suddenly turning the lights on in the Atlantic. Storms that used to be inferred now have visible structure. Their centers, their bands, their development. You can watch a system deepen, its cloud spirals tightening like a screw. You can watch tropical cyclones too, though Britain does not usually receive them intact. You can watch moisture plumes, long, thin rivers of water vapor in the air, feeding storms. The atmosphere becomes less mysterious, not because it becomes simple, but because you can see its handwriting. And still, even with satellites, the forecast is not guaranteed, because seeing the cloud does not automatically tell you what it will do next. It just tells you what it is doing now. With more honesty, now come the computers, creeping into the office without fanfare. Not magic boxes that know the future, just fast calculators that can handle more equations than a tired human with a pencil. The atmosphere is governed by physical laws: conservation of mass, conservation of momentum, conservation of energy. The ideal gas law, relating pressure, temperature, and density. The water cycle, phase changes, latent heat, all the hidden warmth released when vapor condenses. A numerical weather prediction model takes those laws and applies them on a grid. A grid is a compromise because you cannot calculate every swirling eddy in the air. So you divide the world into boxes and you estimate what happens in each box over small time steps. Then you step forward. Again. The computer does in minutes what a room full of humans could not do in a week. But it pays a price. The grid cannot capture every local effect. Small storms, small hills, city heat islands, fog in one valley but not the next. So models need parameterizations, simplified recipes for complex processes, cloud formation, turbulence, recipes that work well enough most of the time, and then fail in very specific and irritating ways. So the modern forecaster becomes a different kind of translator, not just translating observations into a map, but translating model output into a human forecast while remembering where the model tends to lie. Because computers do not remove uncertainty. They industrialize it. They produce a forecast that looks confident, with crisp lines and smooth color fields. And humans, being easily impressed, can forget that those fields are still guesses, just computed guesses. So the culture adapts. Ensembles appear. Instead of one model run, you run many with slightly different starting conditions, because the starting conditions are never perfectly known and small errors grow. The spread of the ensemble gives a sense of probability. If all runs agree, confidence is higher. If they diverge, uncertainty is honest and visible. So the forecast returns in a new form to what it always was, a statement about likelihoods delivered with the best available evidence. You can almost hear the old wartime forecaster snort softly at the modern graphics. Pretty colors do not change the atmosphere. They just make humans feel like they have control. Now, you might think this is the part where we admire progress and call it a triumph. But you are here with me, and I have seen the future, and it is mostly paperwork. The reality is simpler. Today, just like then, the forecast begins with observation. Stations still measure temperature, pressure, wind, humidity. Weather balloons still rise, still burst, still sometimes fail to report. Aircraft still provide data. Ships still report when they can. And the ocean still has holes in coverage. Satellites still have blind spots, and instruments still drift out of calibration. Computers still need good input, and they still produce confident nonsense when fed bad data. So the continuity is the comforting part. No era fully tames the weather. Each era just adds another sense organ, another way to notice what is already happening. And because this is Britain we are talking about, you do not need perfection to be useful. You need a few hours warning that the wind will rise. You need to know whether fog will lift before midday. You need to know if tomorrow will be a day for drying laundry or for pretending laundry does not exist. Now drift back just slightly to that wartime office again, because it is important to feel the scale of what they were doing with so little. They had no satellite loops, no radar mosaics, no instant global models. They had surface reports, upper air soundings, sparse ocean data, and hard-won pattern knowledge. And they still produced forecasts that were often good enough to matter. Not always, but often. That is a quiet achievement, and it belongs to the kind of people history rarely casts as heroes. The careful ones, the repetitive ones, the ones who keep showing up for the next scheduled observation. You sit with that for a moment, and you notice how forecasting is an unusual kind of science. It lives at the boundary between physics and human language. You can compute a pressure tendency, but you still have to decide whether to call it falling slowly or falling steadily. You can plot a front, but you still have to decide how to describe its timing, when it may slow or speed up. You can see a cloud deck on satellite, but you still have to decide whether it will break or just tease. So the forecaster is always negotiating between what the data says and what the listener needs. That negotiation becomes a craft, and it has its own culture. Simple phrases, standardized terms, a calm voice that does not panic even when the map looks ugly, because panic spreads faster than weather. Now, if you keep following this thread, you arrive at the small, private reality of the forecast office. Shift work, night watches, the strange intimacy of sharing silence with someone while reading numbers. You watch a forecaster rub their eyes, not dramatically, just with the tired patience of a person who has stared at isobars for too long. They do not need excitement. They need accuracy, or at least usefulness. And because the work is continuous, the handover between shifts matters. One person briefs the next. Pressure falling faster at the western stations. Upper wind stronger than earlier. Front slightly delayed. Fog risk in the valleys by dawn. This is the office version of storytelling, passing the plot along without embellishment. And if something unexpected happens, if a storm deepens rapidly, the office adapts. Explosive cyclogenesis is the dramatic term, though nobody in a small British office needs the drama. It means a low-pressure system intensifies quickly, pressure dropping fast, winds rising, seas building. When a low deepens quickly, you feel it first as impatience in the data. The western stations report a pressure drop that is too fast to ignore. The wind backs a little, then holds, as if deciding which door to use. Cloud thickens in a way that is not gradual anymore. Out at sea, waves stand up straighter, like they have been called to attention. And in the office, nobody shouts. They just sharpen the pencil and redraw what they thought they knew. This is where forecasting becomes less like reading and more like triage. You do not have time to admire the pattern. You have time to decide how much trouble to announce and to whom. A rapidly deepening low is often fed by contrast. Cold air on one side, warm air on the other, with a strong upper wind helping. The upper flow is the real conspirator. If the jet stream lines up just right, it removes air from above the surface low. When air is pulled away aloft, surface pressure falls and more air rushes in. That inflow strengthens the winds, and the whole system tightens like a knot. You do not need the equations to feel the logic. Take weight off the top of a stack, and the stack rearranges violently. The forecaster watches for this with a tired respect, because rapid deepening can turn a manageable gale into something that breaks things. It can turn a wet night into a night of uprooted trees and downed lines. And in wartime, it can turn a planned crossing into an exercise in stubbornness. So, you hear the phrase deepening used like a warning label. Not dramatic, just firm. Now, while the map changes under their hands, your mind drifts towards something quieter. Because weather is not always about big storms. Sometimes it is about small local trouble that does not show up well on a national chart. Speaking of trouble that hides close to the ground, you return to the most underestimated hazard in Britain: fog. Not the theatrical kind that looks good in a film, the practical kind that makes distance meaningless. Fog is just a cloud that has decided to live at eye level. It forms when air near the ground cools to its dew point. That can happen because the ground radiates heat away on a clear night, or because moist air slides over a colder surface and chills, or because rain moistens everything, and then the wind dies. Fog is not one thing, it is a family of inconveniences. Radiation fog is the classic quiet one. Clear skies, light winds, ground cooling like a stone left outside, The air right above it chills, and water condenses into tiny droplets. At first, it is patchy, sitting in hollows and fields. Then it spreads, thickens, and turns roads into guesses. Advection fog is the traveling kind. Warm, moist air moves over colder water or colder land. The air is cooled from below, and condensation starts. Coasts get this often, especially when sea temperatures and air temperatures disagree. And then there is industrial fog, the dirty cousin. Water droplets form around smoke and soot because particles give vapor something to cling to. This is why coal cities could turn into ghost stories. It is not just water in the air. It is water carrying the city's habits. In the forecast office, visibility is treated like a first-class measurement because in practice, visibility is what people experience. A barometer trend is abstract. The moment you cannot see the end of your own street is immediate. So, visibility is observed carefully, but it is also estimated. Observers use landmarks at known distances. A tree line, a church tower, a hill that either exists today or does not. They report in ranges because nobody can measure fog with a ruler. And the forecaster, hearing those reports, learns how cruel fog can be. Fog can be local and stubborn and oddly precise. One airfield is clear, another 10 miles away is blind. A hilltop is in sunlight, and the valley below is in white silence. So the forecast has to carry nuance without collapsing into poetry. Mist and fog are separated by a threshold, usually about whether you can see more than about 1 kilometer. But the lived difference is more personal. Mist is the world softened. Fog is the world removed. And fog is not just about not seeing. It is about moisture landing on everything. Runways get wet, then slick. Instruments bead with droplets. Glasses haze up, and you blink like it helps. If temperatures are near freezing, fog can deposit rime ice, a feathery crust. That ice adds weight, changes surfaces, and makes a simple thing like a cable or wing behave differently. So when forecasters mention fog risk, they do it like people listing a known nuisance, not because it is small, but because it is familiar. Now, speaking of familiar nuisances that are also physics, you let your attention move to cloud ceilings. Pilots do not care about clouds in general. They care about whether there is room to fly beneath them. A low ceiling means the cloud base is low and the sky is pressing down. Instruments can help, but wartime flying often involves visual navigation. So, a cloud base that drops from 2,000 feet to 500 feet is not a detail. It is the difference between a route and a gamble. Cloud base can be estimated using a ceilometer, a light beam, and timing. Or it can be estimated by trained eyes, comparing cloud bottoms to known heights of hills. Neither method feels satisfying, but both are useful. And at night, under blackout, the sky is even harder to read. You cannot just look up and see the cloud texture. You see darkness and sometimes a faint glow where the cloud reflects scattered light. So, night forecasting has its own quiet strain. The sky is more secretive, and the consequences are the same. This is why upper air observations were so valuable. They gave shape to darkness. A temperature inversion tells you a low cloud deck might persist. A moist layer near the surface tells you fog is possible if winds slacken. A drying layer behind a cold front tells you the clouds might break. So the forecaster keeps toggling between the map and the sounding, between surface reality and upper air intention. And while this sounds very technical, the office life is still small. It is still tea going cold, paper edges curling, and the soft fatigue of night work. Now, let your mind drift sideways into another detail that mattered more than people like to admit: icing. If you are an aircraft, icing is weather turning solid in the wrong place. It happens when supercooled water droplets hit a surface that is below freezing. Supercooled means liquid water below 0 degrees Celsius, still liquid because it has not found a reason to freeze. Then it hits a wing, freezes instantly, and builds a rough skin. That roughness disrupts airflow, reduces lift, and increases drag. The aircraft needs more speed to stay up and more power to maintain that speed. So, icing can quietly turn normal flight into an emergency. Forecasting icing is difficult because it depends on temperature and liquid water content. A cloud at -10 degrees might be full of ice crystals, or it might be full of liquid droplets. The difference matters, and you cannot always tell from the ground. So forecasters use soundings, reports from pilots. Layer clouds near freezing are often suspicious. Frontal zones with widespread cloud and gentle lifting are often suspicious. And if the forecast says icing in cloud, it sounds polite. But what it means is, do not trust the sky to stay soft. Now, since you are already thinking like a pilot, you notice another upper air reality: turbulence. Turbulence is air refusing to stay smooth. It is created by wind shear, by convection, by mountains, by fronts, by jet streams. In human terms, turbulence is the atmosphere hitting you with its elbow. In wartime, turbulence mattered for bombing accuracy. For fuel use, it mattered for aircraft that were already stressed, already heavy, already flying in conditions that were not designed for comfort. Forecasting turbulence is partly physics and partly bitter experience. Strong winds over hills produce mountain waves, invisible undulations that can create severe turbulence downwind. Sharp temperature gradients, especially near the jet stream, can create clear air turbulence. You cannot see it, you just meet it. And again, the office tries to translate all this into calm words. Because even urgent information has to travel through language. Now, you might think this level of detail would be too much for a small wartime office. But remember, forecasting was not only for public comfort, it was integrated into operations. There were specialized meteorological units supporting the Royal Air Force and the Royal Navy. They prepared briefings, route forecasts, and timing estimates. They considered winds at different altitudes because winds determine ground speed. A tailwind saves fuel and time. A headwind eats both with quiet cruelty. So a wind forecast at 10,000 feet is not trivia. It is logistics in disguise. Now, if you follow the thread of logistics, you land in one of the strangest compromises of wartime meteorology. Weather information is useful, but broadcasting it can be dangerous. If you tell everyone the wind is from the southwest at 20 knots, someone listening can plan. So public forecasts were often simplified and sometimes delayed. Yet people still needed some guidance because people still lived. So you get careful phrasing, less specificity, more general trends. And behind the scenes, more detailed forecasts move through controlled channels. This creates a split reality. The public hears unsettled, occasional rain, moderate winds. The operations room hears cold front crossing at 0600, cloud base 700 feet, winds veering northwest, gusting, same atmosphere, different permissions. Now, take that idea of permissions and gently carry it forward in time. Because after the war, forecasting continues to evolve and the culture shifts again. You move from handwritten station plots to printed charts, from telegraph codes to electronic feeds, from a few daily updates to frequent revisions. And something subtle happens. The forecast becomes more present in daily life. People begin to expect it, like a utility. The weather becomes a service, not just a fact. And services create expectations, which creates complaints, which creates pressure on forecasters to sound confident. This is one of the ironies of progress. As forecasts improve, people become less tolerant of errors. A farmer in the 1940s expected uncertainty. A commuter in the modern world expects a percentage, as if a number with a percent sign can negotiate with a cloud. But under the glossy presentation, the same physics still runs. Air rises, cools, condenses, pressure patterns steer winds. The ocean supplies moisture with endless patience. And local quirks still embarrass big models. Now, since you are here for the slow, satisfying texture of how science actually works, let us stay with the modern evolution a little longer. Radar becomes more refined. Doppler radar adds another trick. It can detect motion toward or away from the radar by measuring frequency shifts. This allows meteorologists to infer wind within storms. Rotation signatures can hint at severe weather, even tornado potential in places that get them. In Britain, tornadoes are not a daily worry, but strong convective winds still matter. And even without dramatic outcomes, Doppler helps interpret rain bands and squalls. You can tell if precipitation is organized or if it is drifting. You can estimate where the heaviest bursts are and issue warnings with more precision. Then, satellites diversify. You get water vapor imagery showing moisture patterns in the middle and upper atmosphere. You see dry slots wrapping into cyclones, a sign of mature systems. You see atmospheric rivers, long corridors of moisture that can feed heavy rain. You see dust plumes, smoke plumes, ash clouds from volcanoes, all using the sky as a highway. And this is where meteorology becomes a kind of planetary surveillance. Not in a sinister way, just in an honest one. You are watching a fluid planet breathe. Now, for forecasting, seeing is helpful, but models remain the main engine for looking ahead. Numerical weather prediction improves with resolution. Grids become finer, time steps smaller, physics schemes better tuned, but there is always a compromise. Finer resolution costs more computing power, and the atmosphere is greedy. It has phenomena at every scale, from global waves to tiny turbulence. So modern forecasting becomes an exercise in managing scales. Global models predict the broad patterns days ahead. Regional models focus on local details with shorter lead times. Nowcasting focuses on the next few hours using radar and satellite trends. It is not one forecast anymore. It is a layered system, like the old paper maps, just digitized and faster. And with speed comes the temptation to over-update. If you issue a new forecast every hour, people start to treat it like a live feed. But the atmosphere does not always reward that. Sometimes the best forecast is the same. One, repeated calmly, because the pattern is stable. Other times, rapid updates matter, because a convective line is building and the timing is sharp. So, the forecaster still needs judgment. That human layer never leaves. Now, since we began in wartime Britain, it is worth noticing one more continuity. The observational network is still the backbone. Surface stations, ships, buoys, aircraft, weather balloons, satellites, all of them feed into data assimilation, the process of building the best estimate of the current atmosphere. Data assimilation is the modern version of hand plotting. You take scattered observations, combine them with a model's expectations, and produce an analyzed state. This state becomes the initial condition for the forecast model. And here is the quiet vulnerability. If your initial state is wrong, the forecast will drift, not immediately, sometimes, but like a small steering error in a ship crossing the Atlantic, it becomes large over time. So, the atmosphere still teaches humility. Better tools give you better chances, not guarantees. Now, as you sit with that, you can return to the human texture of forecasting again, because beyond the tools, the job is still a person looking at evidence and choosing words. Even in the modern office, someone has to decide when to issue a warning, when to escalate from likely rain to heavy rain with impacts, when to mention flooding or high winds or snow. And warnings are not just scientific, they are social. If you warn too often, people stop listening. If you warn too late, people get hurt. So warning systems become carefully designed, color codes, thresholds, impact-based forecasting. The focus shifts from what will the weather be to what will it do to people, which sounds compassionate and sometimes is. It is also practical because people do not experience millibars. They experience fallen trees, delayed trains, wet socks, flooded basements. In wartime, the same logic existed, just with different consequences. You did not warn a picnic. You warned a landing. Now, speaking of landings, you can take one more step into the daily reality of how forecasts were delivered then. Radio broadcasts were a major channel. The British Broadcasting Corporation, with its careful tone, carried weather to the public. Forecasts were read in steady voices, designed not to excite. This was intentional, because in wartime, excitement was already abundant. Forecast language had to be calm, and often had to avoid operational detail. So the public forecast became a kind of weather lullaby with sharp edges hidden. Meanwhile, aviation forecasts were delivered as briefings. Pilots and navigators received route winds, cloud bases, freezing levels. A freezing level is the altitude where temperature reaches freezing. Above it, icing becomes more likely. Below it, rain stays rain most of the time. The freezing level changes with air masses, with fronts, with time of day, so it becomes a key part of flight planning. And in those years, with less onboard automation, pilots relied heavily on these briefings. The meteorologist in an operations room was often asked for judgment, not just a chart. How confident are you? How fast is the front moving? Will the fog lift? These questions are timeless and annoying because the honest answer is often probably. So, the meteorologist learns diplomacy, not political diplomacy, atmospheric diplomacy. Now, since the outline of our slow journey wants you to feel the evolution from then to now, you can pause on one more modern detail: the rise of probabilistic forecasting. In the old days, uncertainty was implied in phrasing. Now, uncertainty is often quantified. Chance of rain, 40%. Wind gusts, likely between 30 and 50 miles per hour. Snowfall ranges, with confidence levels. This is more honest in theory, but people are not naturally statistical creatures. Many hear 40% and think it means rain over 40% of the area, or that it will rain for 40% of the day, or that the meteorologist is 40% sure and is therefore morally compromised. In reality, probability of precipitation is a specific thing. It is the chance that a given location will receive measurable precipitation in a given time window. That chance combines confidence and coverage, but the details vary by agency. It is a number trying to compress a messy spatial reality into one digestible bite. It is useful, but it can never be perfect. So the modern forecaster still speaks in plain language alongside the numbers. Scattered showers, meaning not everyone gets wet. Persistent rain, meaning you should not expect breaks. Risk of thunderstorms, meaning the atmosphere is considering violence. And the cycle continues. Observation, interpretation, translation. Now, there is another piece of evolution that often goes unnoticed because it is not glamorous. Communication speed. In wartime, observations arrived on schedules. Forecasts were issued at set times. Today, data arrives continuously, and forecasts can be updated constantly. This is helpful, but it changes the rhythm of the work. The old office had pauses between report times, moments to think. The modern office can feel like a stream, never stopping. You are always watching the next frame, always tempted to adjust, always aware that someone will screenshot the wrong forecast and complain. Congratulations, you have turned meteorology into customer service. But the physical world does not care about customer satisfaction. It cares about energy gradients. So the best forecasters still cultivate the old discipline. They step back. They look for the big pattern. They decide what matters and what is noise. This is the same skill the wartime forecaster used with sparse data. Different tools, same mind. Now, before you drift too far into the modern world, you can let the atmosphere bring you back to something sensory and simple. Rain. Rain is the atmosphere spending its savings one droplet at a time. You do not see the water vapor that came before it. You only meet it when it becomes heavy enough to fall. Up in a cloud, water starts as something too small to feel. It clings to tiny particles, salt from the sea, smoke from coal, dust from fields. Those particles are called condensation nuclei, which is human for places to start. Without them, the air could stay supersaturated, humid, and stubborn, with nothing to grip. With them, vapor has an excuse. It condenses into microscopic droplets, and the cloud becomes a floating archive of near invisible water. You think a cloud is light and harmless. Wrong. A typical gray cloud over Britain can hold thousands of tons of water, suspended by sheer indecision. The droplets are so small that air resistance keeps them hanging. They fall a little, evaporate a little, rise a little, mix a little. It is less like a bag of water and more like a crowded hallway. Everything jostling, nothing committing. Then the droplets grow, and they grow in a few main ways. In warmer clouds, droplets collide and coalesce, which means they bump and merge. A slightly bigger droplet falls faster, hits smaller ones, and becomes bigger still. This is how drizzle can begin, softly, with almost no warning. In colder clouds, ice often does the work. Ice crystals steal water vapor more efficiently than liquid droplets. They grow at the expense of the liquid around them. That process is called the Bergeron-Findyson process, which is human for ice is greedy. The crystals become snowflakes, or pellets, or awkward clumps. If they fall through warm air, they melt into raindrops. If they fall through cold air, they stay solid, and you get snow. If they melt and then refreeze, you get sleet, which feels like the sky throwing gravel. And if supercooled droplets freeze on contact with the ground, you get freezing rain. Congratulations, the world has become a skating rink with no music. Back in that wartime forecast office, rain is not just wetness. It is runway friction and river levels and the slow failure of paper maps. It is also a signal that the atmosphere is doing vertical motion somewhere nearby, because rain usually means air has been lifted. Lift can come from fronts, from hills, from convection, from convergence where winds meet. And Britain, with its coastline and its restless Atlantic, is very good at lifting air. You can feel it in the way showers arrive in lines. A narrow band of heavier rain, then a break, then another band. On the map, it is a front, a boundary sliding across. On your skin, it is a change in the world's mood. The wind swings, the temperature nudges, the light shifts, even the smell changes, from dusty to sharp, from coal to wet stone. If you are standing outside a station, you can hear rain before it reaches you. A faint hiss on leaves, a soft drumming on a tin roof, a rhythm that tells you the droplet size without needing instruments. Fine drizzle sounds like nothing, because it is too polite to admit it exists. Heavy rain has weight, a louder percussion, a sense of insistence. And the forecaster, tired and practical, listens to these sounds too, not as evidence for the chart, but as confirmation that the chart is not lying tonight. Rain gauges give numbers, but numbers arrive after the fact. A standard rain gauge is just a funnel into a measuring cylinder. Simple, honest, and constantly sabotaged by wind. Wind can blow droplets over the top or create turbulence that keeps rain from falling cleanly into the opening. Snow is worse because it can pile and drift and melt later, confusing the time of the fall. So precipitation measurement is always slightly uncertain, which is fitting because precipitation itself is always slightly uncertain. A forecast can say, showers, and still leave you dry. Or it can say, scattered, and still soak the one person who believed it. Now, speaking of belief, you can step into the most important psychological trick of weather forecasting. People do not remember the correct forecast as much as they remember betrayal. If you plan your day around clear skies and get rained on, you feel personally targeted. as if the cloud checked your calendar. In war, that feeling becomes sharper because some plans are expensive. Aircraft operations are scheduled, fuel and crews allocated, windows of visibility chosen. If weather closes the sky, the cost is real. So in those briefings, rain is described with a strange mix of calm and caution. Not just rain, but continuous rain-lowering visibility, or showers with brief heavy bursts, because intensity matters as much as duration. A light steady rain can still allow flight, depending on cloud base. A heavy downpour can erase the runway in gray noise, even if it lasts 10 minutes. And at sea, rain can hide shapes, blur horizons, and make lookouts less useful. So rain becomes part of visibility forecasting too. Visibility is limited by droplets in the air, whether fog droplets or rain streaks. Heavy rain can reduce visibility to a few hundred yards, turning the world into a short hallway. And in convoy conditions, a short hallway is a problem. Ships need spacing, but they also need coordination. So the weather forecast becomes part of formation geometry, even if nobody writes it that way. Now, let your attention drift back to the idea that modern tools changed the craft. Radar, for example, does not just show rain. It shows the structure of precipitation, the bands, the cells, the gaps. But radar has its own limitations, which is a polite way of saying it lies sometimes. A radar beam travels in a straight line, while Earth curves beneath it. So the farther you look from the radar, the higher the beam is above the ground. Close in, you see low-level rain. Far away, you might miss drizzle entirely because the beam is sailing over it, and heavy rain can block the beam, creating a shadow behind it. That is called attenuation, which is human, for the storm is too loud to hear past itself. Then there is clutter, echoes from hills, buildings, and sometimes sea waves. A radar image has to be cleaned and interpreted, not just admired. So even a modern forecaster still does that old work, deciding what is signal and what is noise. Now, step a little closer to the computer side again, but keep it gentle. Modern models produce precipitation forecasts, but precipitation is one of the hardest things to model because it depends on microphysics, tiny droplet and ice processes, plus larger scale lifting. A model grid box might be 1 kilometer across or several kilometers. Inside that box, real clouds are doing complicated things at scales smaller than the box. So, the model uses simplified rules, parameterizations, recipes. Sometimes the recipe makes rain too early, sometimes too late. Sometimes it makes a tidy band where reality makes scattered mess. So forecasters learn to treat model rain like a suggestion, not a decree. They look at humidity fields, pressure patterns, and vertical motion. They ask, does the atmosphere have the ingredients? Moisture, lift, instability, convergence. If the ingredients are present, rain is plausible. If they are not, a model rain blob may be a hallucination. And because this is Britain, the ingredients are often present. So the real art becomes timing and location, the two things humans insist on. When will it start, and where will it hit? The sky naturally answers with maybe. Now, speaking of timing, you can feel the quiet importance of the forecast schedule. then and now. In the wartime office, updates came with observation cycles. A new surface chart every 6 hours, upper air at set times, forecasts issued on routine. That created a rhythm people could work around. Today, you can update constantly, but constant updates can erode trust. So agencies still choose regular release times for key forecasts. There is comfort in a scheduled truth, even if it is imperfect. It gives you the feeling that someone is watching the sky while you are not, and that feeling, more than accuracy, is what many people want at bedtime. Now, without ending anything, you can drift into one of the quieter evolutions of forecasting that rarely gets discussed: the way forecasters learned to treat the atmosphere as an information problem. In the old office, a forecaster drew isobars by hand, smoothing values, rejecting outliers. That was data assimilation, done with human eyes. Modern assimilation does the same concept with mathematics. It merges observations and model background to produce the best estimate of the current state. That best estimate is called the analysis, which is human for our best guess of now. And the forecast is just the analysis pushed forward in time with physics. So all forecasting still depends on knowing the present well. If you misjudge the present, tomorrow becomes fiction. This is why upper air measurements still matter, even in the satellite era. Satellites are excellent at seeing cloud tops and moisture patterns, but they do not directly measure everything near the surface with equal clarity. A weather balloon gives a vertical profile, a slice through the atmosphere. Temperature, humidity, wind at many levels. It is slow and old-fashioned, and still one of the most valuable things you can have, because the atmosphere is not a flat map. It is a layered story, and the layers decide what happens. An inversion traps fog. A dry layer erodes clouds. A strong wind aloft accelerates a front. So even now, someone releases a balloon into the night and watches it vanish. Same ritual, different decade. Now, let us stay with a very British detail because it ties together the science and the lived experience, the way rain interacts with temperature, and how that changes what you call it. If the air near the ground is above freezing, precipitation arrives as rain. But if a layer aloft is warm and the surface layer is cold, you can get sleet or freezing rain. This structure often happens near warm fronts in winter. Warm air slides over cold air, creating a warm nose above a cold surface. Snow forms higher up, melts in the warm layer, then falls into cold air again. If it refreezes into pellets, that is sleet. If it stays liquid but supercooled and freezes on contact, that is freezing rain. Freezing rain is the quiet disaster. It does not look dramatic while falling. It just coats everything. Roads, branches, then things begin to fail under the weight. In Britain, it is less common than in some regions, but it can happen. And in wartime, any extra failure is unwelcome. So forecasters watched temperature profiles carefully when cold air was in place. They did not just ask, will it precipitate? They asked, what will it turn into on the way down? Now, carry that thought into cloud again, because cloud type matters for precipitation. Stratus gives drizzle. Nimbostratus gives steady rain. Cumulonimbus gives showers, heavy bursts, hail, thunder. And the difference is connected to stability. Stable air resists vertical motion, so cloud stays layered and gentle. Unstable air encourages vertical motion, so cloud grows tall and energetic. Stability is decided by the temperature profile. If temperature falls quickly with height, a rising parcel of air stays warmer than its surroundings and keeps rising. If temperature falls slowly, the parcel cools to match and stops. That is the basic idea behind convection. It is not mystical, it is buoyancy. Warm air is less dense, so it rises. Moist air is also slightly less dense than dry air at the same temperature, because water vapor is lighter than nitrogen and oxygen. This is one of the atmosphere's little jokes. Humidity can make air more buoyant, even though it feels heavier to you. Your skin does not measure density. It measures evaporation. In humid air, sweat evaporates less efficiently, so you feel sticky. The air is not heavy, it is just refusing to help. Now, speaking of refusing to help, you can let the story return to the human side of forecasting again. The way forecasts were verified, quietly, without theater. A forecast goes out, then tomorrow arrives, and observations keep coming. Forecasters compare what they said to what happened. In modern times, this becomes statistics, skill scores, bias analysis. In wartime times, it was often more immediate and personal. The airfield report says fog until 1000, but it lifted at 8:30, or it did not lift until noon. The convoy experienced gale force winds earlier than expected. The front stalled, the rain band split. Each mismatch becomes a note in someone's mind, not a scandal, a calibration. Because the craft improves through memory and through consistent checking. And this is where meteorology is more like medicine than people expect. You gather symptoms, you make a diagnosis, you give advice, and then you see what happens. You refine your mental model. You learn what tends to go wrong in similar cases. In Britain, you learn the Atlantic's habits, the typical tracks of depressions, the way a high over Europe can block systems and force them north, the way a high over Greenland can send cold air south, the way the jet stream position changes storminess. You do not need to know every equation to learn these patterns. You just need enough nights watching maps to recognize the mood. Now, let your attention drift toward a specific wartime style detail that is easy to miss: the coded messages. Surface observations were often transmitted in code groups, compressed to save time and bandwidth. Groups of digits represented temperature, dew point, pressure tendency, wind, cloud, weather. To you, it would look like nonsense. To a trained clerk, it was a sentence with no vowels. This compression mattered when communications were busy and sometimes monitored. It also mattered because speed mattered. A delayed observation is less valuable because the atmosphere has already moved. So the network developed a kind of linguistic discipline, a way to describe the sky efficiently. Modern data formats are the descendants of that. Different codes, same goal: to turn the world into transferable symbols. Now, follow those symbols into the computer age again, because the evolution is slow and connected. Once data is digital, you can share it globally. You can ingest it into models quickly. You can run ensembles and generate probabilities. You can produce maps that update every hour. But there is still the same old bottleneck: interpretation. you still need someone to decide whether a marginal snow event is worth warning about, whether wind gusts will reach damaging thresholds in exposed places, whether a flood risk is high enough to mention. Knowing people may panic or ignore it. This is why meteorology, even in the age of satellites, stays stubbornly human. Now, bring it back to the sensory world again, because weather is always experienced, not computed. Imagine you are walking in Britain under a sky that cannot decide. The light is gray, but not dark. There is a wind, but not a strong one, just enough to keep your ears cool. You can smell wet pavement and the faint mineral smell of rain on stone. This is the kind of day a forecast might call changeable with showers. It sounds boring. It is actually a complex atmospheric setup. A cold air mass aloft, a slightly warmer surface, and pockets of instability. Cumulus grows, collapses, grows again. Each cloud is a brief experiment. Some produce rain, others do not. The radar shows speckles, little cells drifting. The satellite shows textured cloud streaks over the sea, aligned with wind. And somewhere, a forecaster watches all this and tries to give you a simple sentence. That is the constant compression from reality to language. Now, if you stay with the science of rain a little longer, you can look at one more subtlety. Why some rain feels cold and some rain feels almost mild. Raindrops falling through dry air can evaporate partly. Evaporation requires energy, so it cools the air. This can create evaporative cooling, lowering temperature beneath a rain shaft. You feel it as a sudden chill when the shower arrives. That cooling can also stabilize the air near the surface, shutting down convection. Or it can create a denser outflow, a gust front, which can trigger new storms farther along. So even a simple shower is not just water falling. It is heat moving, phase changes happening, density changing, winds adjusting. The atmosphere is always redistributing energy. Rain is one of its most efficient tools, and efficient is never the same as kind. Now, shift gently to snow, because even in Britain, snow is part of the forecasting story. Snow begins as ice crystals in cloud. They grow into flakes when conditions allow branching. The shape of the crystal depends on temperature and humidity. Near -15 degrees Celsius, you tend to get more elaborate dendrites, the classic branching snowflake. Near -5, you get simpler forms, needles, columns. But by the time snow reaches you, it has often been through layers that reshape it. It can partially melt and refreeze, creating pellets. It can stick together into wet clumps when temperatures are near freezing. Wet snow is heavy. It loads trees and lines. Dry snow drifts. So the forecast has to distinguish not just snow or no snow, but what kind of snow. And again, this depends on vertical temperature profiles, which is why balloons and soundings matter. Wartime Britain had winters where snow disrupted operations. Airfields became unusable. Roads slowed. Rail lines suffered. And in those moments, the sky's indifference feels personal, even though it is not. So forecasters watched for cold pools, for easterly flows bringing continental air, for blocking highs. They watched the North Sea, which can feed snow showers when cold air passes over relatively warmer water. That creates convection cloud streets, and snow showers that march inland. You can see them on radar now, like beads on strings. Then, you had to infer them from reports and cloud observations. Now, speaking of inference, you can return to the ocean again for a quieter appreciation. Britain's weather is often described as coming in off the Atlantic. That phrase hides a lot. The Atlantic storm track is guided by the jet stream. The jet stream exists because of the temperature contrast between tropics and poles. It is strongest in winter, weaker in summer. Where it sits determines where storms travel. A small shift north can mean Scotland gets the worst of it. A small shift south can mean England gets the rain and wind. So forecasters watch the jet stream.